Okay, hello everyone. We're going to go ahead and start off on organic chemistry with chapter 20. This will be the last chapter on this test section. So we'll continue with chapter 20. So we have chapter 18, which is carbonyls, chapter 19, which is amines, and chapter 20, which is carboxylic acids. But first, just what is a carboxylic acid? So carboxylic acid, remember, is the functional group of C double bond O OH. The most pervasive carboxylic acid you'll see is acetic acid. It's essentially, if we have a carbonyl group and a hydroxyl group, it forms together to form a carboxyl group. Now, a carboxylic acid, there's many different possibilities. You could have a standard aliphatic acid, so you could have aromatic acids, you could have long chain fatty acids, so all sorts of things dealing with it. But they're all going to have some similar properties here. They're all, by definition, going to be acidic. They can act as an acid in basic conditions. When they act like an acid, you're going to form, let's just say, formic acid. So let's start with formic acid in the presence of water. It's going to act as an acid to protonate water and become a carboxylate. So formic acid is going to have a formate NM minus and H3O plus. Now, there's a few common names, some of which it's more common than going with IUPAC, but we try not to use them too much. Like, for example, 12 carbon fatty acids, often called lauric acids. I mean, we have like what, formic, acetic. There's a lot of ones. If a 14 carbon one is myristic acids, 16 carbon acids are palmitic, and an 18 carbon acid is a stearic acid. Stearic. So, I mean, I'm not going to call you on those, but there's a lot of really common names for these guys rather than going like dodecanoic acid or whatever. Instead of trying to count the number of carbons, they often go by just a generic name. The common name is still widely used. Okay. So the first thing, real quick, is how do we name these buggers? Oh, jeez. IUPAC name. So these guys, we take off the E and it goes to an oic acid. Formic acid would be methanoic acid. Methanoic acid. Ethane, or which we typically call acetic acid, would be called ethanoic acid. We had propanoic acid, butanoic. We could do this for days. Benzoic acid would be a benzene, where we take the benzyl group and change it to an acid. we're going to number these guys from the carboxy group. That is the highest priority so far of all the things we've named. So methyl group there and a oral group there. We got to go, okay, alphabetically. This is 1, 2, 3, 4, 5, 6. Our base structure is hexanoic acid. But we have what? Alphabetically, 5 chloro, 3 methyl. So 5 chloro, 3 methyl hexanoic acid. We're going to name this with numbering from the carboxyl. We're naming typically from the most oxidized carbon. So remember, aldehydes took precedence over ketones because aldehydes usually come at the end of the group, and they took precedence over hydroxy groups, and so carboxylic, which is slightly more oxidized than that, takes precedence over our aldehydes and ketones. So, okay. So, as far as we know, the carboxyl will take the highest naming priority of all the different functional groups. So, we're going to worry mostly about that one. So, when it comes to naming. And we can still do the alkenes the same way. If I have, let's say, so okay, that's 1, 2, 3, 4. So that would be butanoic acid. So that'd be trans 2 butanoic acid. Butene acid. And just name that the same way as we would any other alkene. So now we can also have a dicarboxylic acid if we have more than one. Some of these guys have really interesting functional names, and that's really interesting common names. But they're used so often that the common name takes precedence over the normal name. So over the IUPAC names, so such that they actually have a little naming scheme for this. And you could always go ethane, ethane trying to remember how you'd even dicarboxylic acid. 1, 2 dicarboxyethane or something like that. I mean, if we name this guy, okay, ethane version of the dicarboxylic is our oxalic acid. But we have the same interesting. The first, oh my, such good apple pie. Apple pie. See, 2 carbon, 3 carbon, 4 carbon, 5 carbon, 6 carbon, 7 carbon. Where O is oxalic, followed by malonic, succinic, glutaric, adipic, and phthalic. Oh my, such good apple pie. Some of these guys are just, it's easier to say that it's oxalic acid than it is to try to like 1,2-dicarboxy the ethane or something like that. So okay. Now there's also dicarboxylics on benzene, so to make a dibenzoic acid. Those also have a unusual common name. So dibenzoic, you could have, drawing the basic structure, and I'm going to just say like it's coming out of the center because we're not specifying where that's coming out of for its 3 isomers. These guys, dibenzoics, are often called phthalic acids. PHTH LIC or ALIC, phthalic acid. Let me rewrite that. PHTHALIC. Now they're called a different name depending on whether this is ortho, meta, or para-dibenzoic. The ortho-phthalic acid is just called phthalic acid. When we have meta, it's called isophthalic. Ortho is just nothing. The meta, we call it isophthalic. And the para, or terephthalic. So if it's, but how would you name these normally? So now, when it comes to naming these, we're probably going to still stick with the IUPAC, but it's this interesting enough I wanted. So the alkane name for the IUPAC, you would say dioic acid, alkane dioic. Numeric cis. Geez. Second. Okay, so I just need to look that up real quick. Figure out where my notes were. Okay, basically, if I go in the IUPAC name of a so proper way to call oxalic acid with its ethane, you call it. Here's what's weird: we keep the E ending, but we call it the oic acid. We're assuming the ends. The end of each carbon, the end of each chain is our carboxylic when we're naming this guy. So we've got ethane dioic acid. Dioic. So now you could have, this one was interesting enough, I put in my notes, but like we could have the two you would do the still same thing with alkenes. But like say, if you had cis butene versus trans butene, they actually have a different name in common name. So cis butenoic acid, well, so it would be cis 2-butenoic acid, actually is maleic acid. Maleic acid, but trans 2-butenoic acid is actually going to be fumaric. As I said, I'm not going to call you on the names, but it's interesting enough. I felt the need to kind of bring it up. They have completely different properties, such that the cis one melts at 130, the trans one sublimes at 302, but doesn't melt before then. So completely different properties. So now let's look at the properties. Let's look at some of the properties of these guys. As we consider the properties of these guys, the boiling point are typically much higher than alcohols. They are much higher than carbonyls. This is due to a stable hydrogen bond that you can form hydrogen bond dimers with their own, with the molecule. So you can essentially say, oh, hey, I form COOH, but then here's the next molecule, COOH. So it's not just we're forming one hydrogen bond, but we can usually form two hydrogen bonds between two adjacent molecules. And this creates a much more stable liquid and a much more stable solid. Melting point up to 8 carbons are solid, except when it comes to double bonds. So they typically have a very, 8 carbons and up are typically solid at room temperature, except with double bonds. So you guys typically have usually a pretty reasonable melting point. Now, as you can probably expect, they are going to be very soluble in water. Up to 4 carbons are miscible. If you get all the way up to 10 carbons, then you start to become insoluble. Remember, miscible means mixable in all quantities. They are going to be, of course, extremely soluble in alcohols. It's going to be pretty hard not to dissolve them in alcohols, because the fact that you got the hydrogen bonding, you also have that organic groups as well. But also, these are going to be quite soluble in many non-polar solvents, such as chloroform, as you can still keep some of those dimers. So carboxylic acids are soluble in a lot of different solvents. They're not necessarily limited by what they can dissolve in. Now, when it comes to acidity, most will act at least weakly acidic in water to form carboxylate. So the basic weak acid dissociation to form hydronium. Now, they are less acidic than typical inorganic acids, but they still are acids. So I'm saying HI, HCl, see like sulfuric acid, nitric acid, all these guys are going to be stronger acids, stronger by far, but they still count as acids. Acetic acid is still an acid. Benzoic acid is still a reasonable acid. They're going to be stronger acids than the alcohols at the very least. Now, part of the reasons why they're going to be such strong acids because the conjugate base is going to be stabilized by the resonance structure. So just drawing here, O minus, we can imagine, oh, we have an equally stable resonance structure of R O minus. So we have this resonance stabilized intermediate, this resonance stabilized anion is going to be why these are going to be so willing to dissociate. Now, if you have, one thing to keep in mind is diprotic. So dicarboxylic acids will, of course, have two dissociations to worry about. They'll have two pKa's. So if I'm looking at oxalic acid, I'm going to lose one of my two protons first, and then I'll lose my second proton. Now, hopefully you remember your general chemistry that the first dissociation is always going to be much, much greater than the second dissociation. Because once you have that anion in there, you have to get a second anion in there, and that's going to be a lot harder to do. This is going to be, this second loss is going to be created by the repulsion of two negative charges that are being so close together. Even though this can resonate back and forth between the oxygens, when a negative charge between here and here, it's going to be, you have a lot of repulsion you got to worry about. So obviously that's going to be mitigated, you think, by long chains and whatnot. Anything that will stabilize the negative charge will make this better, such as electron withdrawing groups. If I put fluorines in there, that's going to pull away the electron density of this and stabilize these. So if I have fluorines close to these carboxylates, it's going to make it more stable. If we make a lot of them, it'll be more stable and thus more acidic. So, I mean, obviously, if I have a choice of, say, drawing a, if I have a choice of when the fluorine here versus here, this guy is going to have a larger effect than this guy, because it's going to have, you have to pull inductively that negative charge through a shorter distance to get to that fluorine. When we have benzoic acids, so like our phenyl acids, or ortho and para directors like methoxy will decrease acidity. Meta directors like nitro will increase acidity, because remember, what are they doing? Electron withdrawing versus electron donating. So knowing that, if I can, we have this negative charge, this guy is going to be less acidic than because this guy's electrons pushed into the ring. Nitro group, which is a positive charge, is going to be pulling electron density out of the ring. So just think about that. Think about that electron density pulling out, electron withdrawing group, going to stabilize this acid, make it stronger acid. Electron donating group, going to weaken that acid. So keep in mind, depending on the situation, these acids can be pronated and depronated. If I put this in a basic surroundings, we're going to form our carboxylate salt. If I put it in acidic surroundings, we're going to reform the acid. This is going to be a very useful property, for example, when you have when you want to separate the two. You want to say, oh, I want to remove this guy from solution by making a salt. I'm going to put this guy back in solution by reacidifying. So this is often a thing that's done the same way as a protecting and deprotecting. Looking at salt nomenclature. So how would we name it? We're going to name this much like an ionic salt solid. The only difference is that when whatever the name for the organic, for a salt, we're going to call it the metal, whatever the metal is, and the name, or alkane, whatever it was, and instead of oic acid, it would go to O8. So for example, if I reacted sodium hydroxide with propanoic acid, 1, 2, 3 carbons, it would form water, of course, because acid plus base gets water, and sodium propanoate. And because sodium propanoate. This is going to be similar to how we're going to name esters later. Because essentially we have the ester group, except instead of saying methyl propanoate, we're saying a metal propanoate, whether this is sodium, lithium, potassium, cesium. You could have magnesium propanoate if you would of course have 2 magnesiums. I mean 2 acids. Now our salts, when we go to look at the properties, our salts, the most soluble salts are going to be with salts with lithium, sodium, potassium, and ammonium. These guys are going to be always soluble. Of course, our rules in general chemistry were these ions were always soluble with anything. But most other metals are insoluble. Soluble with most other metals. So, for example, hard water will screw this up. Soap scum is an example of this. Magnesium, when we make soap a little bit later, magnesium with our R group, this guy is going to essentially solidify out as our soap scum. That's why you never seem to get clean in various hard water solutions, because of the essentially soap dissolves and then precipitates on your body, and it doesn't really easily wash off. Now, these salts are usually highly soluble in water, and they're poorly soluble in organic. But so the idea here is that if you know how to use these salts, you can use this to separate acids from solution. Say you start with organic with acid, and you want to remove the reactants from the products. So step 1, you basify, add base. And then so there you have organic, and you have aqueous. And then this gets removed. Then we acid. And so there's organic acid and aqueous down here. Of course, you remove the aqueous. You dry your organic acid off with sodium sulfate, and voila, you have pure acid with very little difficulty because of this salt properties. The fact we can acidify and basify with very little difficulty. So, okay. More properties. So like when we look at IR, when we look at our spectroscopy, IR, it can be sometimes be confusing, but IR should contain a carbonyl group and an OH group. But the carbonyl has been typically shifted a bit, and the OH is usually shifted quite a bit, from 3,500 to 2,500. It's usually shifted quite a bit over, so it's usually actually creeping into our CH stretches. So if it seems to have shifted a bit from where we usually see it, and it's with a carbonyl group, there's a good chance that the carbonyl and hydroxy are right next to each other. Still, it can sometimes be deceptive and we don't always notice it. So that's where NMR is super helpful if we know how to look for this. Now, mind you, proton NMR, not always very easy. Proton NMR, not very easy. I mean, the OH can still show up anywhere. It could be sharp, could be broad, could be, the OH could be anywhere from 10 to 13. You might not really see it. And the CH adjacent, so the CH alpha to these guys are going to be between 2 and 2.5 shifted based on the fact how close they are to the the carboxy group. So this is kind of a little bit crapshoot to try to read this, but C13, there's usually a pretty dead giveaway in that. So alkenes are usually between 160 or less to 100, sometimes 120 for alkenes. Carbonyls are usually between 200 plus. So right dead in the middle is our carboxy group. These guys are between usually 170 to 180. These could be ketones. These could be esters. They could be amides. They could be carboxylics. But they're right in the middle, really, really high up there, and they're usually a dead giveaway that I have, especially if I see this OH stretch in the IR. It's usually a dead giveaway. Oh, I have a carbonyl. It'd be really useful. And of course, the alpha carbons nearby see a 30 to 40 ppm shift. So you see a pretty significant shift from these guys. So there's usually the carbon 13 is the best bet on noticing these guys. Now, there's some UV vis stuff, like these guys will like show up in the UV vis, especially with conjugated alkenes and diconjugated alkenes, but we haven't really covered the UV vis real well, and so I'm going to leave that out. We're not going to worry about that. Okay. Now, we'll go ahead and start some of the synthesis here. Looking at the synthesis of these guys. Some of these guys we've kind of covered before. We can oxidize these guys with primary and secondary alcohols. Well, primary alcohols and aldehydes. We can oxidize these guys. So like for example, so primary alcohols. with unoxidizing reagent like bleach or dichromate, some sort of chromic acid. We can push this all the way to carboxylic. Now, so like H2CrO4, I mean, it's going to go through a aldehyde intermediate, but aldehydes are actually going to be more reactive than our alcohol, so they're going to keep reacting so long as there's enough reactant to do it. All the way to go to acid. So, I mean, that's a pretty simple way to turn from that. We've also discussed things like cleavage of alkenes. We've seen this before where we essentially hit an alkene with really strong oxidant and kick its ass. So, really strong oxidant like potassium permanganate, another oxidation one. That, remember, if I have an alkene like this, and I hit it with cold, dilute. So we weakened our permanganate. We weakened our oxidant. We essentially form a dihydroxy. But if we instead had done warm and concentrated, we just snap it off and just like, holy crap, I've just kicked the Jesus out of this, and we form the fully oxidized products. Now this guy, because it was, sorry, I'm just trying to show I'm cleaving that. Because that guy would have formed an aldehyde, it keeps oxidizing to the carboxylate. And because this guy would have formed a secondary alcohol, it stays as a ketone. But so like any monosubstituted carbons on the alkene can go all the way to carboxylic. And we could just straight up cleave an alkyne. So I'm going to go ahead and delete this and redo all these. So an alkyne, of course, they're all going to be monosubstituted. So these guys are going to wham, bam, thank you, ma'am, go all the way. So like if I just say, so I could use this with our potassium permanganate, or I could have used, if you remember, ozone. Our good friend ozone could also ozone with water. And what, like our oxidant. Essentially, what do? You oxidize these guys to a very unstable diketone. And then you keep oxidizing and cleave this. Goes to our dicarboxylics. Obviously, if the functional groups are different on both sides of the alkyne, we get two different carboxylic acids. But so far, we've just talked about oxidation. Oxidation. Let's see. Oxidation of alkyl substituents of a benzene. This is the last one we'll talk about, and I'll maybe call this class a little early. But just so we end up on a like a good ending point. So oxidation of alkyl substituents of a benzene. So remember this. This is using harsh conditions on a benzene. Benzene is really hard to react with. You need special reactants to do this. So this is safe. Remember, this was safe for chlorines, nitro groups, sulfuric acid groups, and other carboxylic acid groups. But like alkyl groups, we reacted with something with like hot permanganate. Or we could have done hot chromic acid. But essentially, what did you do? Under acidic conditions, we kick that all the way down to a function. It doesn't matter what this functional group is, we annihilate it down to a 1-carbon carboxylate, 1-carbon carboxy group. If this was a 5-carbon chain, it's 1 carbon now, baby. That's all it is. So, okay. So we're going to end it there, and I'll pick up in a little bit, and we'll continue with some of the ways we're going to make these acids. But we'll go ahead and end it there for now. So this has been the Chemistry Cowboy. Once again, if you like what you see, please like, please subscribe. I'll be posting more videos to give you the education you need. And I've been asked to put this disclaimer to Bethel students. Remember that the log and the online learning guidelines remain in effect while interacting with any type of instructional materials / sessions. That over and out.